Hello, everybody. So what I want to talk about today is an extension of what we've already been talking about, and that is how do you correct or how do you account for the fact that monomers in a real system interact with a solvent and also with each other. And as we've talked about, the implication of this is that the size of a polymer chain is going to deviate from what we consider the ideal limit, whether that's a freely jointed chain or whatever. Okay, so there's a couple things to remember. The first thing to remember, some of these concepts that we need to keep fresh in our mind, is that when we had the ideal chain models, there were key assumptions that went into those models, and that's why I keep saying this over and over again. It's not the equations that matter. It's how you get to the equations. Obviously, you have to be able to use the equations, but that's not the important part. The important part is that we understand where they come from and how to use them. So that's kind of what I'm getting at here. When we talk about ideal chains, it's not just that the size of the chain R scales as n to the 1/2, and also Rg scales as n to the 1/2. It's not just that. What else is also important is that the free energy from that, the free energy of an ideal chain, is due entirely to entropy. So polymers are big balls of entropy, and the chain statistics that we get, the fact that R scales as n to the 1/2 power, is just due to entropy alone. So another way to write this is that the entropic free energy of the chain, as a function of its size and its degree of polymerization, and we derived this last semester, the free energy is basically kBt, so thermal energy, and then multiplied by a factor, and that factor is 3r squared divided by 2nb squared. And now you should know what all of these terms are. So that's the free energy from entropy. And if you wanted, you could calculate the entropy of the chain, right? Because that's going to be minus the partial derivative of that free energy with respect to temperature, holding a number of things constant, holding basically everything else constant. So that's an important concept to realize. So for an ideal chain, it's due to entropy only, or its shape, I guess, is due to entropic, or is entropic in origin. And the free energy has this term that is due entirely to entropy. And we went through that derivation, right? We took a random walk and we calculated the number of microstates, and we took the natural log and so on. So that's the first concept that's going to be important for today's video. The second concept that's going to be important to today's video is that polymer chains are self-similar. What on earth does that mean? Well, if something is self-similar, it means it looks like itself. Sounds weird, right? But what it means is that if I have a polymer chain like this big wiggly thing, then let's characterize it some way, and maybe we can characterize it this way by looking at maybe the magnitude of its end-to-end vector. And we saw on average that will be 0 for an ideal chain, but we can look at maybe the average of that thing squared. All right. Now, in the notation that we've used so far, that r squared, so this thing, we can drop the vector notation since it's squared. I basically call this r squared. We're going to get rid of those brackets that denote that we're averaging over many chains. And we know that this is basically b squared times n. All right, so we spent a lot of effort on that last semester. Now, if something is self-similar, then it means that it looks like itself. At smaller length scales, the chain is going to look the way it looks at big length scales. So across these different length scales, the chain is going to look the same. So what I can do is I could blow up a region like this and look at it. And so if I do that, I'm going to try to draw it the same way that it's drawn there. So in that region, my polymer chain would look like that, sort of. So if something is self-similar, then what it means is that I can look at its end-to-end distance here, and I'm going to call it something else. I'm going to call it the Greek letter C, xi, and I can look at the value of that squared. So again, this is Greek letter xi. It's probably the hardest one for me to say. But we're going to use that to denote length scales that are smaller than the size of the chain. So if I was to do that, and if in this region I had, let's see, little g monomers, then this, the size here at the small length scale would be b squared times g. Okay. This might look familiar to you when we were talking about blobs, the blob theory, or the blob way of looking at polymer chains. So what we'll do today is this small region here. Typically what I'll do is, let me just draw another one here. So typically this small region here is what I'm going to call a blob. And then when I look at it like this, then I'm going to talk about what its size is and how it looks at these smaller length scales. Okay. If you were in class with me, you would know that I'm a notorious coffee drinker, so I'm going to be drinking coffee in today's video. I kind of feel better about that. I watch a lot of YouTube videos. I watch usually physics things that I don't remember as well from undergraduate and graduate school. So I watched videos by Sean Carroll, who's the guy at Caltech that I basically stole this style of video from, and Leonard Susskind, who is famous for string theory. And when I'm on campus, I usually go to the Sage's Cafe when it was open, and I would get coffee there. And of course, they have Pete's Coffee from San Francisco. And Leonard Susskind is at Stanford University, and when he's lecturing, he always has a big cup of Pete's coffee. And I was like, oh, wow, okay. The good people, or not the good people, but the people I look up to in physics do this too, so it can't be that bad. Anyway, little digression there. But anyway, these are the two concepts I want you to remember for today, that ideal chains, their free energy is due entirely to entropy, and that polymer chains are also self-similar. All right, move this up. Okay. So let's go back to what we talked about in the previous video. A polymer chain is real. A polymer chain has, let's just say this, a real chain has excluded volume. So that's going to be the difference today. Excluded volume can be positive or negative. If it's negative, don't get freaked out by the fact that the volume is negative. Don't worry about that. If it's negative, it just means that things are getting way, way, way close together. Things are getting crumpled up. If it's positive, then things are getting bulked up. So if that's the case, then the free energy due to interactions, and let's just say for a chain that has, let me use the same notation, a chain that has a size R and has N monomers, that free energy, we're going to have to make it an intensive value, right? That's kind of what we did last time. So this free energy that I've drawn here is for one chain. So this free energy is actually going to be the free energy per volume, but I'm just going to call this F with interactions of R and N, but keep in mind that it's scaled by volume, okay? So what are we going to do? Well, we need the free energy of a polymer chain, of a real polymer chain. So this is the Flory theory that we're going to use today. It's by Paul Flory, Nobel laureate in chemistry for his work on polymers. And what this theory says is that if I want the free energy of a real chain as a function of R and the number of monomers that are in the chain, then this will be the sum of the free energy due to interaction, so due to excluded volume, and it's going to be the free energy that is due to entropy. So one way of thinking about the Flory theory is that we started with a theory for an ideal chain that's based on entropy, and now we're adding a correction term, and it's not a correction term actually, but we're kind of correcting our theory for the fact that there are interactions and that chains do have a finite size. So this is actually going to be, though, the free energy per volume because of this reason that I laid out here. Okay, so if you look back to the notes from last time, and I could scroll up and do it, but I'm not going to go there. You will see that we normalize that by the volume. Okay, so we have this. We have the free energy due to entropy, and we have the free energy due to interactions that we derived last time by expanding it, by taking a virial expansion. So we expanded the free energy in terms of the concentration, the number of monomers per volume. So if that's the case, we can combine these terms, and this free energy will be kBT, again, the thermal energy, multiplied by the free energy that's due to the interactions between monomers, and the free energy that's due to entropy. And so neglecting higher order terms right now, actually, let's not do that yet. Let's just write down what we have. So this was the excluded volume multiplied by n squared over r cubed, and then plus this term w multiplied by n cubed over r to the 6th power. That's the interaction term. All right. So this part here is due to interactions. And now we have to add the entropic term. And so that's pretty easy. We'll just add to this. And I should say there are higher order terms here that we're not going to mess with. But added to the interaction term will be plus this thing up here, right? This thing, the free energy due to entropy. And we've got the kBT out front, so that's good. So we're just going to put this second term into the brackets. So that will be plus 3/2 times r squared over nb squared. And close the bracket. And just to be very clear here, this is due to entropy, that term. All right? Now, before we go any further, let's think about this. Oh, I'm having such a bad hair day. What do we want in nature? Or what do natural systems prefer? I shouldn't say they prefer anything, right? They just exist. But in nature, things tend to having the lowest value of their free energy. So if we look here, if we're looking at the size of the polymer chain, which is R, the interaction term is going to be minimized if the chain is very, very small, regardless of the value of those coefficients up front, right? Because as R goes to infinity, then those interaction terms would contribute less and less and less to the free energy. I should say those terms are not minimized if the polymer gets small. Those terms are minimized if the polymer gets big. So if the polymer is big, those interaction terms go away. Look at the entropic term. The R squared is in the numerator. So entropy is preferring a big chain. Big chain, big ball of entropy. So these terms are acting in opposition to each other. All right, so I haven't said anything about W yet. Let me just say what W is before we neglect it. In a polymer chain, I've been drawing the polymer like this. And what we've been talking about so far is what happens to the size of the chain due to interactions between pairs of monomers. So these are two-body terms. So those two-body terms are giving you the excluded volume. And you saw in detail in the last video how that happens. W, right here, is a three-body term. So the three-body term is due to this interaction and that interaction. So it includes interactions between three particles. So these are three-body terms. We're going to neglect them, but the thing is, with polymer chains, if you look at this expression, we're going to, I'll talk about it in a second, okay? I'll talk about what the three-body term is going to do, but we're going to neglect it for now. So let's neglect three-body terms. And I'm going to give you a homework problem to practice with the three-body term. But if that's the case, then W is equal to 0. And you can see if W is equal to 0, then this term would go away. Okay? So if that's the case, if we neglect the three-body terms, then the free energy for a chain with size R and with degree of polymerization N, normalized by the volume, will be KBT times V times N squared over R cubed. That's going to be the interaction term. And then plus 3 R squared over 2 NB squared. And that's due to entropy. So this is essentially the Flory theory. It's not entirely correct, actually. We found out later that it's not actually correct, but it does give a result that's close to what we measure experimentally. All right, so now the question is, what do I do with this? Why do I care about this free energy? Well, the reason is that I can get the size of the chain from it. How? Well, in nature, F will be minimized at equilibrium. Promise you, if a system's at equilibrium, then the free energy must be minimized. When is something going to be minimized? F is minimized think back to calculus. The function is going to be minimized with respect to R if the derivative of F with respect to R is equal to 0. And that derivative will be 0 when the chain has a size that's equal to its equilibrium size. So when RF is the size of the chain, then the partial derivative of that free energy with respect to R, evaluated for R is equal to RF, will be 0. Pretty good. So we just have to do that. We're going to take the derivative of that equation, set it equal to 0, solve for r, and that will be our f. So let's do this. I'm going to flip my notes over so that I don't make a mistake while we do this. And let's take the derivative. So let's do that. The derivative of f with respect to r is going to be equal to 0, or that's the condition that we want. And that will be equal to kBt times, do this yourself, check my math. All right, it's good practice. You'll have to do it on the homework anyway. This will be from the first term, 3v with a minus sign because r is in the denominator, n squared over rf to the fourth, because remember, this derivative is equal to 0 when r is equal to rf. And then plus 2 rf over nb squared. All right, so the 2 comes down, I get a 6. 6 divided by 2, did I screw that up? 6 divided by 2, actually that's a 3. Good God, my core. See, when I was doing these videos and doing the voiceover live, I could fix these mistakes. Now I have to really make sure I don't mess up. Well, that makes a lot more sense. All right. So whatever. It's a scaling theory. I don't care about these things. So let's divide by 3 right off the bat. So, boom, done. I don't care. All right, so clearly the thing in the brackets has to be 0. So that means that V, the excluded volume, times n squared over rf to the fourth must equal rf over nb squared. Right? And now we just have to solve for rf. So rf, I'll just multiply through to the 5th power, will be the excluded volume times b squared times n cubed. Hope I did that right. Well, this is easy. We'll just take the 5th root. So rf will be v to the 1/5 power, b to the 2/5 power, n to the 3/5 power. And that's it. That's the size of a chain. We're assuming here that v is greater than 0, right? Let me clean that up. But we're assuming that v is greater than 0. So we're assuming if v is greater than 0, we're assuming that the chain's in a good solvent or an athermal solvent. So this is for good solvent conditions. Not fantastic solvents, not excellent solvents, good solvent conditions. So another way of saying this is that R scales as n to the 3/5 power in a good solvent. Okay? 3/5 is 0.6. So you'll see me doing that too. This is something that I care quite a bit about. This is something that my group measures with neutron scattering. We care about what the scaling of a chain is. So when I say the conformation of a chain, what I'm really referring to is what that power is. Now, Flory's theory gives us a result that you can verify experimentally. I've done the experiments, and loads of people have done these experiments with neutron scattering or X-ray scattering or light scattering or whatever. That 3/5 power is pretty close to what we get. But if you take a more sophisticated approach, and we won't do it, it's pretty difficult. There was a Nobel Prize awarded for it. It shares, the There are commonalities between magnetism, quantum field theory, so calculating things with Feynman diagrams and whatnot, and calculating the scaling exponent for a chain and a good solvent. Turns out that in 3 dimensions, nu is equal to 0.588. So that's the actual value. You can see that it's close, but it's not quite the same. So this was done with renormalization group theory. And we won't talk any more about it. It's a mechanism for approximating something in a series and then truncating terms, basically. But this is the exact value. So this is exact. So you can see I've got this scaling here for an ideal chain. R scales as n to the 1/2. So in general, what we'll say is that R scales as n to some power nu, and I shouldn't say equals, but nu is going to be approximately equal to 3/5 in a good solvent. Nu is going to be 1/2 in a theta solvent, or a polymer melt of ideal chains, so just a system where you only have that polymer, a block of molten plastic. And nu is going to be something else if it's in a poor solvent. And we'll talk about what that something else is. Okay, so that's the Flory theory. Now, you can see I got the size of the chain by taking the derivative and setting it equal to 0. If you wanted to do this for a theta solvent, remember, if you have a theta solvent or a melt, what does that mean? It meant that the excluded volume was 0. Okay, well, try to do that. Try to make v equal to 0, take the derivative, and set that derivative equal to 0, and try to solve for the size of the chain. It's not going to give you a really nice value. You're going to get that the size of the chain is 0. So what does that mean? It means that the chain wants to collapse. Well, that's not right, because we know that's not right. One reason is that we derived the size of the chain using a different method. The other reason is that I can put a polymer chain in a theta solvent and I can measure it, and I find that my chain still exists. It has to have a size. So that's where W comes in. So W, that 3-body term, is our savior here. It stabilizes the chain. And so you'll have a homework problem where you put in a non-zero value of W and go through the same kind of derivation and see what the scaling of the polymer chain is. And so you will find that R scales as n to the 1/2 if you have no excluded volume, but you still have the 3-body term. Okay, so it's important, but for the good solvent case, we just kind of neglected it because it already has the n to the 1/2 scaling. So we wanted to see what actually the scaling would be because of the excluded volume. All right, so that's that. And so the only thing we have to do next is we want to see what happens in the poor solvent case. And then we know almost everything there is to know about polymer chains, except maybe what happens when they're grafted to nanoparticles or when they're grafted to a surface when you form a polymer brush. In that case, it's going to be a little bit different. We will talk about it, but we won't talk about it in this video. All right. So how do we do this? Well, I'm not going to talk about the poor solvent first. First thing is I want to just talk about the polymer chain in general. So here's my polymer chain. They tend to always look the same when I draw them. And remember, polymer chain is self-similar. So I'm going to break it up into blobs. So here's the blob. Come on, give me my circle. There we go. Okay. All right, so each blob is going to have G monomers, and it will have a size equal to that Greek letter that I don't want to say. I wish it was Chinese, right? Then I could just say shi, so like shigua, watermelon. All right, so that's where I'm going to start. Now, if a chain has excluded volume, if it's going to be swollen, so the chain will be swollen if what? If its excluded volume is greater than 0. When is its excluded volume going to be greater than 0? Well, in a good solvent, but more importantly, when is that going to contribute to the size of the chain? That is going to contribute to the size of the chain if the free energy term that's due to interactions, which is equal to kBT, I should say this divided by volume to be correct, which is equal to kBT multiplied by the excluded volume times n squared divided by r cubed is greater than kBT. Why? Thermal energy is just these random kicks that the polymer chain gets when it's in the solution or in the melt. So if this term is to contribute to the size of the chain, then it had better be bigger than kBT. Otherwise, it's just going to get lost in the wash. So another way of saying this is you can neglect excluded volume if the free energy term due to interactions is less than kBT. Right? So if this term is less than kBT. Right? All right, that's fine. So what does that have to do with blobs? Well, I can go back to the blob and I can construct a thermal blob. So this isn't just a blob, this is a thermal blob. And so this thermal blob also has a free energy on the order of kBT. That's an assumption that I'm making, but certainly there is a blob that has a free energy of kBT. I mean, there has to be. If this blob is too big, then I just make one smaller and smaller and smaller until that blob has energy kBT. So that's going to be my thermal blob. So it's kind of an assumption, but there's nothing ridiculous in that. So, all right, that's fine. Well, if that thermal blob has a free energy of about kBT, then I can ignore the interaction term. So the thermal blob only has a size that's due to entropy. All right, that's fine. Well, if its free energy is only due to entropy, then that means the size of my thermal blob is given by the entropic term. And we've already done that, right? It scales as n to the 1/2. So that means that the size of the thermal blob, which is equal to this, let me make this a little thicker. So this thermal blob here has that size, then it's only due to entropy. So that means that this will be B, the Kuhn length, times the number of monomers in there. And if you want, you can put a T because it's a thermal blob. If you're following along Rubinstein and Colby, that's the way that they denote it, to the 1/2 power. All right. And the free energy is basically the free energy due to entropy. And it's due to kBT. Right? All right. Let me flip my notes here. So, again, we're going to assume that F due to interactions divided by volume, if you want, is much, much less than kBT in the thermal blob. So we know its size. Of course, I could square this. I'll just write it down, even though it's obvious. But this squared will be B squared times G thermal, just for completeness. All right. So I've got that. So now what? Well, I'm not quite done yet. This was the entropy term. What happens at the very limit? So if I have a very, very small blob, so let's say that the size of the blob is very small, then the free energy will actually be less than kBT. So it's only going to be equal to kBT when I have GT monomers. So if this would mean that G would be less than GT. So I add more and more monomers to my blob. I bulk it up more and more and more. And eventually I reach the size of the thermal blob where I get this. Remember, I only have a thermal blob if the interaction term is going to be less than kBT. So what does this mean? This means that at the thermal blob size, the interactions just become important. So just when this interaction term is about kBT, I can estimate what that would be, right? So this term F int divided by V is equal to the excluded volume times kBT. Well, I just plug in what I've got. So I've got GT monomers squared divided by R cubed. Well, what is R in this case? R is the size of the thermal blob, so it's this value. So I've got that. That's the size of my thermal blob, and that's what I get for the, what am I trying to say here? That's the size of my thermal blob, and that's what I get for the interaction free energy. Oh, my hair. Right? All right, so I've got this. I can solve it. What do I want to do? Well, this is also going to be equal to kBT, right? Just at the boundary where the interactions start to play a role, that term is going to be about kBT. If it's less than kBT, I don't care. But right when it starts to become kBT, or right when it's about kBT, that's where this term can no longer be neglected. It starts to play an increasing role in the size of the chain. So if I just take these terms here, I can solve. So I get V times GT squared over that cubed is equal to 1. Or the point that I'm trying to get at here is that I can solve for GT. If I plug in, let me just do that. I don't want to skip a step here. I know the size, so this means that the size cubed will be B cubed GT to the 3/2. So I can plug that in here. So again, I don't want to skip steps. Let's just do it. I get GT squared over B cubed GT to the 3/2 power. And so I can follow this through and solve for GT, and I'll let you do that. B to the 6th over V squared. In fact, maybe I'll make that a homework problem. Show me that that's true. Okay, so if you're doing the homework, here's your homework hint. You can do it here. All right? Simple algebra. Okay, so I can plug this value back into the expression for the size of the thermal blob. And I'll see that the size of the thermal blob then will be b to the fourth divided by v. And let's be careful. Let's make this the absolute value of v. All right. Okay, lots of math. What does all of this mean? Well, let me first do the poor solvent case, and then we'll go from there. So now we can do the poor solvent case. We're going to come back to this. This is very important. And I'll show you what it means on a graph in a second. But now with this information, we can use this to do the poor solvent case. So what do you expect in a poor solvent? Let's think about it. It means that the interactions between the monomers and the polymer chain, the monomers and the solvent, that interaction is unfavorable. The result of that, following our discussion in the last video, is that there's a very strong attraction between monomers in a poor solvent, right? So there's some interaction between monomers. There's a very unfavorable interaction between the monomers and the solvent. So the result of that is that there's an effective attraction between the monomers. So there's an effective, strong attraction between the monomers. Okay. So if I have a polymer chain that looks like that, what happens if there's a strong attraction between the monomers? So all of these guys and gals are going to be attracted to each other because they don't want to be in contact with the solvent. Okay, so that will lead to a smaller chain. It's going to be collapsed. So the result of that is that my polymer chain will be crumpled up. It'll form a globule. Now, for those of you interested in biomaterials and applications of biomaterials, this is a really important thing. So if you think about polynipam, so poly N isopropyl acryl, oh my God, amide. That's why we call it nipam. This happens. This is called a coil. So if I write it in terms of this drawing, this is a coil. And then if I heat this up so that T is above 32 degrees C in water, the chain goes from being a coil to being a globule. So we call this a coil to globule transition. So it's very important. And so the idea is that, well, what's your body temperature? Your body temperature is around what, 37 degrees? So if you have a polymer chain that's in a syringe in buffer, now don't do this, polynipam will kill you if you inject it, but that's beside the point. If it's in a syringe, if it's in buffer, which is mostly water, you inject it from room temperature into the body at 37 degrees, then it will be above 32 degrees, which means that you'll trigger a shape change in the material. If you trigger a shape change, maybe you can trigger drug release or something absorbing or better transport through capillaries or who knows. But it's a nice handle to tune the properties of your material when you go from room temperature into the body. But that's the thought anyway. Okay. So if it forms a globule, what are we going to assume? Well, we're going to assume that we've got this globule with a size R globule, and that it will be a dense packing. So again, poor solvent, V is less than 0. We're going to have a dense packing of the blobs. So if I blow up my globule, as in magnify it, not if I magnify my globule, I don't want to make it too big. All right, here's my globule. Let's put a circle around it so that I know this is my globule size. There we go. So if I have a dense packing of blobs, then that means that inside I've got literally a dense packing of the blobs. And I'm not going to draw all of them in, but you kind of get the picture here, right? They're all going to be packed in. So this is my dense packing of blobs. Cool, can do that. All right, so the volume of this globule, 4/3 pi r globule cubed. What's the volume of a blob? Well, each of these blobs here has its size, which is given by the expressions we've been talking about all throughout this video. So the volume of the thermal blob will be 4/3 pi times their size cubed. So clearly this means that the number of blobs that you have is going to be the total volume divided by the volume of a globule. And so if you do this, if you assume that also, well, you don't have to assume anything, but you know that there's going to be, what am I trying to say here? Let me see. I skipped a step here. That is not true. I'm getting ahead of myself. The number of blobs that you're going to have, each blob has GT monomers. Your polymer chain has N monomers. So the number of blobs you have is going to be the number of monomers in the chain divided by the number of monomers in a blob. That's what I meant to say, not the volumes. All right, now we can talk about a dense packing, because the number of blobs multiplied by the volume of a thermal blob should be the volume of the globule. That's what I meant to say. And I know the number of blobs that I have, so I've got N divided by GT, and I've got 4/3 pi C cubed is going to be 4/3 pi r globule cubed. Right? Just setting the volumes equal to each other. That's what I mean by a dense packing. If it wasn't a dense packing, that's not true. Well, I love it when this happens. Boop, boop, boop. Those go away. And so now I've got almost the expression I want. I need to make some substitutions. I need to make the substitution that the number of monomers in a thermal blob is going to be b to the 6th divided by v squared. So that's why we did that discussion about KBT and when interactions are important and when they're not important. So I've got the number of monomers. And what else do I need? I need that the size of the thermal blob is going to be b to the 4th divided by the absolute value of the excluded volume. So I've got a lot of volumes in here. So those are the excluded volumes in these expressions. Right? Because absolute value is in this expression because V is negative in the case of a poor solvent. And so now I've got cube here, so I can take the cube root. I can substitute these in. So this goes in here, and this goes in here. And I clean up the expression a bit. So I'll let you do that on the homework maybe. But when I do that, I'm going to get this expression. I'll give you some intermediate steps. I get b to the 4th divided by absolute value of v. And then I get excluded volume to the 2/3 power divided by b squared. And then I get n to the 1/3 when everything cancels out. And so this is going to give me b squared divided by absolute value of the excluded volume to the 1/3 power, n to the 1/3 power. So this is poor solvent. All right. Now, before I go on, I want to emphasize this is important. Literally, my group used this expression to construct a new theory, and it was published in December 2020. So this is stuff that gets used all the time. It's in a textbook, yes, but it's important. It's not like it's just in there and we never use it again. This is important stuff. But now we can fill in our chart a little bit. So remember, R scales as n to the 1/2 if n is less than the number of monomers in a thermal blob. R scales as n to the 1/2 in a theta solvent or a melt of identical chains. R scales as n to the 3/5 power in a good solvent, and R scales as n to the 1/3 power in a poor solvent or a non-solvent. All right. Difference between poor solvent and non-solvent. Poor solvent, there might be a tiny bit of solvent in here in the globule. Non-solvent, there's not going to be any solvent in there. It's like, screw you, I don't like you, I'm not going to hang out in your globule, thanks. All right. So you can see, if you've learned in 270 the size of a polymer chain, you might have learned this and this. But the size of a polymer chain is actually a lot more complicated than that. And R, let me just say this so that we're complete in our discussion here. R scales as n to the nu power in general. This is called the Flory exponent, or the scaling exponent. And if you have a polymer brush, those are useful. Nu will be greater, messy. Nu will be greater than 3/5. And this is something that my group's working on right now. What is that value? Turns out it depends. Depends on a lot of things. All right, so that's complete. Let's not talk about this now, though. We'll talk about this later. So the last thing I want to do is show you a graph about how complicated polymer conformation can be. So if R scales as n to the nu, then if I plot log R, I'll get nu log n plus a y-intercept. Okay, so what? Well, let me draw a plot. Let's plot log R, and we'll plot this as a function of log n, or we could plot this on a log-log scale, but I don't really want to draw a log-log scale because I'm not so good at it. All right. Let me also move this label down. There we go. Oh, I love this app. Thank you, Sean Carroll at Caltech. Thank you. All right. So let's start talking about the conformation of a polymer. Well, let's start plotting it for n. If n is less than gt, then the slope will be what? Well, the slope here will be nu, and nu will be 1/2. So I'll get this and the slope here will be 1/2 up until the point that I've got GT monomers. GT, I always think of my Mustang GT. Love that car. All right. Sorry, digression. That's the trouble with live lectures or semi-live lectures like this, is you're going to get to hear all of my digressions about how much I love sports cars. Okay, so now what? Let's plot the next case. Let's say that the polymer chain is in a theta solvent or it's in a polymer melt. If that's the case, and I get that line. Slope is still 1/2, but this is going to be theta solvent or melt. It's implied, but let me just be explicit. This slope is still 1/2. So far, so good. What if it's a good solvent? Well, if it's a good solvent, then what? The slope should be 3/5. So after the thermal blob, I'll get this. The slope here is 3/5. Actually, it's 588 if you care about the details. And this is a good solvent. And then let's put it into a poor solvent. For the last case, well, we just saw that the slope is 1/3. So this slope is going to be 1/3. And that's a poor solvent. So that's that. Those are the simplest cases of the limits of polymer conformation. Like I said, if we have a polymer brush, then it's a little bit more complicated, and it depends on molecular weight, and it depends on a lot of things, basically. It depends on grafting density and all sorts of things. And we'll talk about those cases in an upcoming video. We won't derive them, but we will talk about them so that you're aware. So that's it for now. Next videos, we're going to talk about things like deforming a chain. We'll talk about brushes and things like that.